Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Asad Abbas. In this lecture, we will compare different quality assurance activities and techniques by examining their cost, applicability under different environments and development phases, and their effectiveness in dealing with different types of problems. So, we start our discussion with comparison of quality assurance activities and techniques. It is important to mention that to compare a particular technique with some other techniques, we need to have some evaluation or comparison criteria. Therefore, here the criteria that we will be using for comparison of different quality assurance techniques is that includes their effectiveness in dealing with various types of problems. Similarly, costs for performing those quality assurance activities, and the applicability of those quality assurance activities under different environment and different development phases. In fact, a comparison of quality assurance alternatives together with related techniques and activities is a cost benefit analysis under the overall environment for software development or long-term maintenance. Therefore, to start comparison, typically there are some questions to be asked and some comparison criteria, as I mentioned in the previous slide, to be defined. So these questions and comparison criteria could be classified into three broader categories, that is environment, effectiveness, and cost. And we will have our discussion in the upcoming slides based on these criteria. So we first discuss the questions and criteria related to environment. The main question is the applicability of uh, specific quality assurance alternatives and the related activities and techniques to specific development and maintenance environment. We can first divide our examination of the applicability question into two general environments, that is the development environment and the maintenance environment. The maintenance environment, we mean that which includes operational support and software maintenance activities. Most of the quality assurance alternatives have a development focus. However, the applicability to software maintenance may vary in several ways. For example, first, the defect prevention activities, they're typically not applicable to the software maintenance process. Although the lessons learned or the experiences gained from related activities can be used for future defect prevention activities. Then inspection, formal verification, and testing can be applied to a very limited degree to software maintenance process. For example, when a problem is reported by some customers, we can perform related inspection, verification, or testing activities to locate the problem as well as to ensure that the fixing of the problem indeed would correct the problem. Then defect containment alternatives such as fault tolerance and failure containment apply to software that is in operation, that is in execution. Therefore, they can also be applied to the software maintenance process. However, the design and implementation of these features are supposed to be completed during the development process. The focus during the software maintenance process is the support for normal operations and damage reduction, but not fixing problem or correcting the underlying software products. Here we will discuss the effectiveness of different quality assurance alternatives by examining the qualitative and quantitative information from different perspectives. First we will discuss the defect perspective. From that is Here we ask some questions. For example, like, is the quality assurance technique dealing with errors? Is it dealing with faults or with failures? This question can be broken down further with the execution observation of the specific quality assurance activities and the follow-up actions where different defect perspectives may be taken. For example, as can be seen here in the upper figure, that during testing, failures are observed, which lead to follow-up actions to locate and fix the faults that caused these observed failures. Similarly, during inspection, as we can see, faults are observed, and the follow-up actions include the fault removal. A detailed comparison of different quality assurance techniques from the perspective of their ability to deal with the various defects is given in the figure at the top. Then another perspective that closely relates to different defect perspectives are the problems or like types of defects. Uh, uh, for example, as we can see in the lower figure, that uh, dynamic problems are typically associated with some uh, interface or interaction among different parts of the software products, which might be more easily detected through testing than through inspection. On the other hand, logical and static problems may be more cost effectively detected through inspections. Similarly, different quality assurance techniques may be suitable for different defect levels or different levels of pervasiveness. By pervasiveness, we mean that presence of defects or their density in different modules or different program parts of the programs. For example, as we can see in the figure at top, that if defects are pervasive in the system, then systematic inspections might be more appropriate than testing, because inspection can continue after some defects are detected, unlike in the case of testing, which often needs to be stopped once a failure is observed. Similarly, another perspective in context of the effectiveness is the ease of result interpretation and constructive information. This plays an important role in the application of specific quality assurance techniques. In fact, a good understanding of the results is a precondition to follow-up actions. For example, both inspection and testing are aimed at defect removal. However, inspection results are much easier to interpret and can be used directly for defect removal. Testing results need to be analyzed by experienced software professionals to locate the faults that caused the failures that were observed during the testing, and only then can these faults be removed. In addition, re-verification of defect removal is also more complicated in testing than in inspection. Additional testing effort in the form of reruns or re-execution is typically involved, while re-inspections are less likely to be are required. And even if they are required, it would be much simpler to perform. On the other hand, result interpretation for formal verification, fault tolerance, and failure containment is harder than that for inspection and testing. Sometimes a significant amount of effort is needed to analyze these results to support the follow-up actions. For example, in a fault-tolerant system using recovery blocks, repeated failures need to be dealt with offline by analyzing the dynamic records. Much information needed to unanticipated environments and usage not covered in the pre-planned testing activities may be included in these records. The difficulties with interpreting formal verification results usually involve the formalisms used, which require formal training, not formal training, not as readily available to software practitioners as other quality assurance alternatives. In comparison, defect prevention produces results in the form of reduced fault injection, which is harder to quantify or visualize. However, we do not usually associate direct follow-up actions with them except packaging the experience for future projects. Therefore, the difficulty with interpreting defect prevention results is in fact less of an issue. In addition to easy result interpretation, we would like to have different quality assurance alternatives to provide as much information as possible to help us improve quality for the current and future products. So here we can see that in the bottom figure, in the right column, we have some type of information, constructive information that can be provided by these quality assurance alternatives. All quality assurance alternatives can be potentially applied to all kinds of products. However, for different products or market segments, some might be more important while others are less so. For example, fault tolerance and failure containment are appropriate for market segments where high dependability and safety are major concerns, while they may be too costly for some low cost entertainment software. Similarly, defect prevention activities, as can be seen in this figure, are performed at different stages of development. For example, requirements, design, etc. Likewise, inspection can be carried out during all the development activities and so on. Here we discuss the participants' expertise, that is, the expertise of people who are performing the quality assurance activities. The factor of people's expertise, including people's prior education, skill, experience, and on-job training, affects the applicability of specific quality assurance techniques. This factor also affects the overall cost directly because good fit between the people's expertise and the specific quality assurance activities to be performed would in fact incur little additional costs beyond the professional's time. As we can see in this figure that different quality assurance alternatives may require different levels of expertise and background knowledge. For example, checklist-based testing requires a low to medium level of expertise and may not require any background knowledge. On the other hand, defect prevention typically requires good knowledge of the application domain, the development methodologies and processes and tools, etc., to be effective, thus requiring medium to high levels of expertise. Similarly, a formal verification, fault tolerance, and failure containment require high expertise and sufficient education and training to effectively apply these techniques. Then the third criteria we discuss for the comparison of different quality assurance techniques is cost. If the total cost can be calculated for each quality assurance alternative, then it can be used together with the benefit assessment to select appropriate ones for a specific environment. The quality cost can be mainly categorized into direct costs and indirect costs. The direct costs for carrying out the planned quality assurance activities typically involve the time and effort of the software professionals who perform the related activities and the consumption of other resources such as computer systems and like other supporting resources or facilities. In addition, there are also indirect costs such as training the project participants, like acquisition and support for related software tools, meeting time, and other overheads. All these costs should be considered in our decision to choose the appropriate quality assurance alternatives. There are several factors affecting the mentioned total costs. Sometimes it is easier and more straightforward to deal with these factors instead of dealing with the cost directly, because some of these factors are more closely related to individual quality assurance alternatives. Some key factors related to this include, for example, simplicity and availability. So we will discuss each of these factors in the next slide. So the first factor is simplicity of the techniques associated with the specific quality assurance alternatives. A simple technique is generally easy to understand, easy to use, and easy to perform, and more likely to be supported by existing tools. Moreover, minimal amount of training is needed before a software quality professional can learn and master these techniques. Therefore, the simplicity of the technique will affect the total cost of the selected quality assurance alternative. For example, inspection is much simpler than formal verification, thus costing significantly less effort and cost to perform as compared to the formal verification. Then availability of tool support. In fact, this is the second factor, and it has a significant influence on the cost of specific quality assurance alternatives. This is particularly true for our current software industry, where the share of and the cost of professionals' time is dominant on the other costs, such as the material costs. Consequently, availability and affordability of software tool support is an important issue, because such automated support would save software professionals valuable time and allow them to perform other tasks as well. Most of the traditional quality assurance activities such as testing and inspection, focus on defect detection and removal. The cost can then be directly related to the effort in detecting and fixing the problem. Another part of cost not commonly considered is the cost of downstream damages caused by the dormant defects or those defects that escape the collection of, for example, quality assurance activities. However, this cost is negatively correlated with the effectiveness of the of different quality assurance techniques, particularly the quality levels at the exit after the application of a variety of quality assurance techniques. Therefore, we focus on the cost of defect detection and removal as well. Another complication to the cost evaluation and comparison is the defect prevention techniques, which prevent the injection of certain faults by spending valuable resources to block the errors or to remove the error sources. The reduction in defect injection is in fact hard to measure or quantify. Therefore, we focus on the costs related to the effort to prevent fault injection. For the case of fault tolerance and failure containment, the cost includes three parts. That is the operational costs, implementation costs, and failure or accident costs. So the failure costs, first of all, let's discuss the operational costs. The operational costs include the cost of having specific mechanisms in the operational systems, which may slow down the overall system and reduce the system's capacity or may negatively affect other performance measures of the system. For example, repeating failed execution in the fault tolerance implementation using recovery block slows down the usual normal processing of the system. Then implementation costs, which is in fact the second cost here. Uh, uh, this includes like cost to design, implement, and assure selected features and mechanisms such as backups and redundancies. Failure or accident cost, which is the third cost, that is similar to the dormant defect cost considered that we just discussed for defect prevention and defect reduction techniques. So here is a cost comparison for different quality assurance alternatives. We see that the cost for defect prevention they are low, whereas testing has medium costs. Similarly, techniques, for example, inspection, that also has low to medium cost, whereas the cost for formal verification, fault tolerance, and failure containment in fact, they are rather high, and we see that failure containment that actually has the highest cost of all of these quality assurance alternatives. So that's all about our discussion on the comparison of different quality assurance activities. The comparison of the applicability, the effectiveness, and costs of these quality assurance alternatives that we just discussed in this lecture that can help software professionals select or choose the appropriate quality assurance alternatives and related techniques, and so that they can tailor or integrate those techniques from the perspective of their specific applications. The materials in this video are based on our coursebook titled Software Quality Engineering, Testing, Quality Assurance, and Quantifiable Improvement by Jeff Tian. For more details, you can consult the book. Thank you.